Chapter 9, and we're only doing a couple sections in there, so we're almost done. Section 9.1 is on antiderivatives. So I have a question for you. If y equals 3x to the fourth plus 2, then what does y prime equal? Well, that should not be a problem at this point in the game. We're just taking the derivative of this, just have to use the power rule. Bring the 4 down, multiply by 3, we get 12x cubed. And of course, the derivative of a constant like 2 is 0. So don't even need to put it. There you go. Finished. But what if I gave you the derivative? What if I told you that y prime equals 6x squared? Could you figure out what y equals? Could you figure out what the original function equals? Okay, instead of this 2 dropping down to a 1, as normally happens when you do the power rule, what's going to happen to the 2? It's going to go up. It's going to become x cubed. Alright, well, what number is going to have to go up front here? Well, I think if you look at it a little bit and do a little bit of calculation, you could figure out that what should be up front here is a 2, right? Because if you do the power rule, if you go to the opposite direction, 3 times 2 is 6x, and this would drop down 1 to 2, so 6x squared. So there you go. But here's the thing. There could actually also be another piece to this, couldn't there? You could have plus, and what could go right here? Anything, as long as it's a constant. So I'll put C, and then I'll write could put any constant here. So what we just did here, where we started with the derivative and found the original function, if you want, takes us to the idea of antiderivatives. What an antiderivative is, it's also called indefinite integrals. It's the reverse process of differentiating. So that's probably the easiest way to think of it. You're just doing the opposite direction. But mathematically what that looks like is if f prime of x, so if the derivative of capital F equals little f of x, then, now here's a new symbol, f of x dx equals fx plus c. Whoa, what's going on here? What's this all about? Okay, this big S looking thing, this is called the integral sign. This alerts you to the fact that you're going to take an integral. You're going to take an antiderivative. The f is the integrand. It's like the function that you're taking the integral of. The x is the variable of integration. The c is the constant of integration. Capital F of x is the function you end up with. The only thing we haven't talked about that yet is the dx. As for this dx here, I'm going to give you a very unsatisfying answer. You can think of it as, for an integral, there's the starting sign, which is this s, I think it comes from sigma, but I'm not going to get into that either. But there's this sign here, and that the dx is kind of the ending part of the notation, and that everything in between, the fx, is what you're taking the integral of. So that's a very unsatisfying answer. This idea that this is just like a full stop at the end of it. There's actually a more complicated, I would say quite a bit more complicated reason for this. It has to do with we're taking smaller and smaller pieces of x, and we're looking at the area of different rectangles under a curve. I just don't want to get into it right now. Okay, you'll learn about it in university. We can talk about it in class, but I'm just going to leave it for that. Okay, so in other words, I'm just going to say again that think of it, I think for now, even though it's not a totally satisfactory or correct answer, a lot of people, actually I think I went through all through university and never always thought of it this way, is that this is your starting and this is your ending of the integration notation, and anything in between those two highlighted bits is the bit that you're actually taking the integral of, that you're actually taking the antiderivative of. Okay, let's move on. So, some commonly encountered antiderivatives. If you had the function 0, what would be the antiderivative? So in other words, you know this already, what sort of function, when you take the derivative of it, do you get 0? Well, we already talked about that. When you take the derivative of any constant. So a function of 0 has an antiderivative that's a constant. What if you have a function of 1? Well, what do you have to take the derivative of to get 1? You take the derivative of x. So the antiderivative of 1 is x. Okay, here's a harder one. What's the antiderivative of x to the n? Well, you know it would be x to the n plus 1. But would that be it? No, it wouldn't actually. Let's go back up here. Remember this example we said right here, this 6x squared? If all you did was raise that 1 and put 6x cubed, you wouldn't have the right answer. You need to end it with a coefficient of 2 here. So to see what you'd do to the 6, you would actually divide it by that same amount, by 3. And this will work every single time, as you shall see. So it's going to be x to the n plus 1 divided by that same amount, n plus 1. In fact, let's take a look at one of those right now. Let's say we want to take the antiderivative, or the integral, of x cubed. Okay, so remember, the s and the dx just tell you we're taking the integral. It's x cubed, which we're actually taking the integral of. So according to this formula, what I do here is I would raise this 3 to 1 more, which is x to the 4, and it would also divide by that same amount. I divide by 4. So is that correct? Well, let's think about this for a second. Let's go the opposite way now. If we were taking the derivative of this, what would you do? You'd move the 4 down. The 4 would now become a 3, and it would still be, of course, over 4. Hey, wait a minute, those would cancel, you'd have x cubed. It worked. So this will always work, this formula that we have right here. Before I go any further, let's just make sure you're clear what we're talking about. What we're saying is that if I'm taking the integral of 4x cubed, or the antiderivative, same thing, if I'm taking the antiderivative of 4x cubed dx, the answer to that would be what? Well, you'd raise this to the 4th power, so you'd have x to the 4th, and you'd also divide by the same amount, so the 4's would cancel. This would be your answer. If you're not clear about that, try going the other way. Try taking the derivative of this. The derivative is 4x cubed. That's exactly what we have. But you'd also have to put plus c, because remember, you could also have any constant there, and when you take the derivative of that constant, it would equal 0. So if we go this way, we are taking the integral. We're doing integration. If we go this way, this is what we've been doing this whole course. This is taking the derivative. So they're just opposites of each other. Opposite processes. Okay, let's move on. 1 over x. Which function has a derivative that's 1 over x? Do you remember which one? It's the natural logarithm of the absolute value of x. How about this? Which function has a derivative which is e to the kx? Well, you know that the derivative of e to the x is just e to the x, so you might think this is just e to the kx. But that k is definitely going to impact things. Like, let's say, for example, you were taking the integral, the antiderivative, of e to the 2x, and then I'll put that dx to close off the integral notation. Well, you might just think it's e to the 2x, right? But let's go the opposite way. If we went the opposite way, if we actually take the derivative, it would be e to the 2x. It would be the chain rule, wouldn't it? It would be e to the 2x, but then we'd have to multiply it by the derivative of the inner function, so that would be 2, and that's not what we have here. So what would we have to do to get that answer? We would have to divide by 2. Oh, so it looks like what we actually have to do is we have to divide this by whatever that amount is, that k. So in this case, we'd have to divide by 2. And that would give us the right answer. Because, again, if we try, right, you can always try by taking the derivative. You'd have a constant of 1/2, so you could just write that, right? Then you'd have e to the 2x, that's your outer function, and your inner function, the derivative of 2x is 2. Hey, this and this would cancel, you'd have e to the 2x, and that's exactly what we wanted. So this is our formula for when we have e to the kx. Cosine of kx. Okay, so what do you take a function of and you end up getting cosine x? It's sine x. If you take the derivative of sine x, you get cosine x. But wait a minute, this is cosine kx. So let's think for a second. Sine kx. Why don't we try taking the integral, the antiderivative of cosine 3x dx. So again, you think, okay, well, it would be sine 3x because we're going in the opposite direction. But this isn't the right answer yet, is it? Because again, if we went backwards, if we took the derivative of sine 3x is cosine 3x, but then you'd have to multiply by the inner function, the derivative of the inner function, which is 3, and we don't have that 3. How come? Because we must have divided this by 3. So your formula for this is sine kx over k. Okay, sine kx. You might think this is just cosine kx, but remember, cosine, when you take the derivative, it's going to be negative sine. So in order to get sine, you must be negative cos. And again, that's not enough. You're going to see that you have to divide by k. Let's take a look at that. If we had sine 2x dx, so again, you might just think it's cosine 2x. Let's start with that. But when you take the derivative of cosine, you get negative sine. We want it to be positive sine. So it must be you must need to have a negative here. So when you take the derivative of cosine and get negative sine, negative sine is positive sine. Make sense? Now, even this isn't good enough, because taking the derivative of this would give you positive sine 2x, but then you'd have to multiply by the derivative of the inner function, which is 2. And we don't have that 2 there. How come? Because we must have divided it by 2. That way, when we multiply by the 2 from the derivative, it cancels out the 2 in the bottom. So this is why you have that k on the bottom. Okay, let's try some examples here. Find the antiderivatives of all the following. So we're starting with f of x equals 4x cubed minus 6x squared plus 11. So remember, we're trying to find the antiderivative. We're not taking the derivative here, we're doing the opposite. So often the way we write this is, since this is f of x, I'll say capital F of x to represent we're doing the antiderivative. We're taking the integral. So what were our rules when we're doing, what's like the opposite of the power rule? We're going to raise that 3 up to 4, and then we have to divide by that same amount, by that 4. So same in the next one. We're going to raise this 2 up to 3, and then divide by that same amount. What would happen here? Well, if it helps you think of this, this is like this. There's no x here, so it's like x to the 0. I guess you can't even see that. X to the 0. So we'd raise that up to 1, so it'd be 11x to the 1, and we divide it by 1, but you don't have to show division by 1. So anytime you just have a constant, just slap an x on the end of it, and that'll be good. Now, one more thing. You have to also say plus c, right? Because any constant would also work. Once you take the derivative of that c, that constant, you just get 0, so it would work. All right, let's simplify this, and then we'll check our answer. F of x equals, the 4's cancel, top and bottom, so you get x to the 4th. The 6 and the 3 cancel, you get 2x cubed. There's nothing else you can do. So let's make sure this works. How do we check it? We just see what the derivative of this is. The derivative of this would be 4x cubed, yep, minus 6x squared, yep, plus 11, yep, and then plus 0. The derivative of a constant is just 0. So you do have to put that plus c in there every single time. Okay, next one. I mean, we just practically did this on the other side, so this is very repetitive. The antiderivative of cosine is, you can check the table that we just did if you want, is sine. So sine x. Takeaway. Now, what's the antiderivative of sine x? Negative cosine x. So it means our final answer is going to be f of x equals, sine x plus, take away negatives plus, cosine x. You don't have to, but it is good when you start doing these, check your answer. The derivative of sine x is cos x. The derivative of cosine x is negative sine x, and there's that negative sine x. So it worked. What did I forget? I'll forget this all the time. I bet you I'll forget this in at least 2 more of the questions. I forgot to put plus c. Good for you. Good for those of you who noticed it and were screaming at your computer or your phone. Okay, here's one with e's in it. So we want to get the antiderivative. And what we have is negative 3e to the negative x. And remember what our formula was, is we just keep this exactly the same, this e to the negative x, but divide by whatever number it is right here, which is negative 1. So you can have negative 3 e to the negative x, but you got to divide by negative 1. And same here, you'd have 6 e to the 2x, but you got to divide by the number right here in front of the x by the 2. So let's simplify and check. Negative divided by negative is positive. Don't need to worry about the 1 there. So 3e to the negative x plus 6 divided by 2 is 3e to the 2x. Okay, let's try. Let's take, oh, I almost forgot again. Almost caught myself before I finished my circling job here. Don't forget the constant. So if we were to take the derivative of this, it would be 3e to the negative x, but we'd have to multiply by negative 1 because the derivative of the inner function. So we'd have negative 3e to the negative x, negative 3e to the negative x. Perfect. Then for this one, we would have 3e to the 2x, but then we'd multiply by 2, the derivative of the inner function. So this would become 6, 3 times 2, 6. 6e to the 2x, 6e to the 2x, exactly, plus c, because the derivative of a constant is just 0. Done. Okay, next one, you probably want to start not by taking the antiderivative, but by actually rewriting this. Why don't we rewrite this as 2x to the negative 2 minus 5 times 1 over x. I know that's weird. Why didn't I make it 5x to the negative 1? I'll talk about that in a second. Plus x. Okay, now we can take the antiderivative. So what's our rule here? We raise this up 1, so 1 bigger than negative 2 is negative 1, and we divide by that same amount, that negative 1. Why did I do this? Because we can't have x to the negative 1 here. Like if I'd written 5x to the negative 1, I'd raise it by 1 and get 0, and then divide by that same amount 0? What? You can't do that. So what's going on here? Well, we talked about on the other side in our chart, what is a function that when you take the derivative of it, you get 1 over x? That's that natural logarithm function, isn't it? So this must be negative 5 times the natural logarithm of x. Plus, now we can just use our power rule, our reverse power rule, raise this by 1, you get 2, and divide by the same amount. And I remember my constant this time. Okay, simplify. 2 divided by negative 1 is negative 2. X to the negative 1, might as well put it back into the denominator, minus 5 times the natural logarithm of x, plus x over 2, x squared over 2, plus c. I think this will work. This is negative 2x to the negative 1. I'm just going to write that down here. So the negative 1 would come down and make it positive 2x to the negative 2, which is the same as 2 over x squared. So that definitely works. Second one, we'd have minus 5 is a coefficient, so that can just stay up front. Natural logarithm of x, the derivative is 1 over x. So you should have negative 5 over x, yep. And this one, if you were taking the derivative of this, the 2 would come down, would actually cancel with the other 2, and then this x squared would become an x to the 1. So it worked. Okay, these last two are hard. I'll just be honest, they're hard. And it's because there's some chain rule going on here. So what you need to notice, like first of all, hopefully you notice that this is hard. It's like, whoa, how am I going to do this? This is crazy. And then there's something to notice here. What you want to notice is that the derivative, so d dx, of the denominator, 3x squared minus 8, what's the derivative of that? The derivative is 6x. Hey, that's exactly what the top is. The top is 6x right there. So this is your hint that you're probably going to use the chain rule, right? You're probably going to do something to get 3x squared minus 8, and then when you multiply by the inner function, take the derivative of that, you get the 6x. So what would make this 3x squared minus 8 end up in the denominator? Well, something ends up in the denominator when we take the natural logarithm of it. So let's try this out. What if we did the natural logarithm of 3x squared minus 8? Would this work? Well, if I go the opposite direction, and just so I don't forget, I'll put plus c in here, right here. So if I was to go the opposite direction, take the derivative, I'd first of all take the outer function, which is the natural logarithm, and I'd take the derivative of that. That means 1 over the inner function, so 1 over 3x squared minus 8. Then I'd look at the inner function, and I'd take the derivative of that, which is 6x, and I'd multiply. Well, wait a minute. 1 times 6x is just 6x. You get 6x over 3x squared. That's exactly it. We have the right answer. So when you have these complicated ones, if you can notice something that's the derivative of another piece, you're probably going to have the chain rule. And I think that happens in the next one too, because we have sine x cos x. You're like, sine x cos x, what are we going to do here? Well, again, notice that the derivative of sine x is equal to cosine x. So again, one piece is the derivative of the other, so we're probably using the chain rule here. So this cosine x must be the derivative of the inner function. In other words, the inner function must be sine x. Well, how could that be the inner function? Like, what else would we put to give it an outer function? But let's put a 2 here. Now suddenly you have to use chain rule for this, don't you? Because if you take the derivative of this, you'd first of all do the outer function, the 2 would come down, and you'd have 2 sine x, and then you take the derivative of the inner function, which is cos x. But wait a minute, we said it would be 2 sine x, and there's no 2 here. Oh darn, how could we get rid of that 2? How about divide by 2 here, and this should work. Want to check it? Why not? We already kind of did, but let's do it again. So the outer function is something squared. So you're going to use a power rule. The 2 comes down, and it's now just sine x. Then you have to multiply by the derivative of the inner function, which is sine x. Well, that equals cos x. And don't forget, you have this 2 here, so it's kind of like the whole thing is times 1/2. These cancel, you're left with sine x cos x, and that's what we wanted to start with. By the way, what if, way back at the start, you'd said, I just noticed something. The derivative of cosine x is negative sine x. Could you still have done this? Yes, you could have. It would have been very similar, except you'd have to have an extra negative. Because, for example, in this case, your inner function, or your derivative of the inner function, would be the negative sine x, or the sine x here. So what you'd start with is cosine x, but you'd actually want it to be squared again to get that chain rule in effect, and divide it by 2. So let's see if this works. If I take the derivative of this, I'd bring 2 down, right? Outer function first, the squared, the 2 would come down and cancel with that. I'd be left with cosine x, and then I'd multiply by the derivative of cosine x, which is negative sine x. So I have negative sine x cos x. Oh, but I don't have negative sine x cos x. I just have positive sine x cos x. So what could I do? Slap a negative right on here. This is equally as correct. Either blue or purple works in this case. Of course, the constants wouldn't be the same. So if you want, you could call this C2 and C1 here, because the constants wouldn't be the same. Alright, tricky stuff. Takes a while to get used to.
Take a little trip, take a little trip, take a little trip and see.